We ended last week with the idea about what uses variability, and I had pointed out that standard deviations would start to become extremely important. So we're going to learn a little bit more about those now. So here we have our normal distribution, and you can see that it's broken up into some pieces. Along the bottom, at the center near the mean, we have the mu, and then also to the right and to the left, you can see that there are standard deviations being added and subtracted to that mu. So each of these represents a point on the axis that cuts off a certain percentage of the standard distribution. So you can see that one standard deviation above the mean and one standard deviation below the mean cut off that blue area in the center. And in total, that blue area accounts for 68.2% of the data in a normal distribution. And this is just one of the rules of the normal distribution. If we go out one standard deviation further, so that we're also now cutting off the red areas, you can see that we've added 13.6% on either side for a total of 95.4%. So what that means is that approximately 95% of the data in any normal distribution is going to fall within plus and minus 2 standard deviations. The other 5% is going to come in the extreme tails on either side. This is where there's not a lot of data in the distribution. Generally, we consider any point that falls into these tails as extreme scores, scores that have a low probability of having come from the standard distribution or the standard curve. The other idea in this week's homework is the z-score. A z-score is one of the kinds of standard scores out there, and in general, they have two purposes. The first purpose is to find out where any specific single score falls within a distribution. You might be able to tell if you're above or below the mean, but the z-score will actually help you know how far above or below a mean a particular score is. So for example, if we had Maria, who's 26 and graduating from college, and she wants to know how old she is compared to the other graduates in her class, a z-score could be used to figure out just how far above or below the mean she was. But the more common purpose for the standard score is a z-score standardizes data to compare from different distributions. So we can compare scores that came from two separate distributions, two separate data sets, even if they have different means and standard deviations within each of those data sets. So as an example, if we had Johnny, who is getting ready to go to college, and he scored an 1150 on his SAT and a 22 on his ACT, and we wanted to know which one he did better on, we couldn't just directly look at the numbers because they come from different distributions with different means and different standard deviations. What we could do, though, is we could calculate a z-score for each test and then directly compare those z-scores to draw a conclusion about which test he did better on. To find a z-score, the formula looks like this. You would take the data point, which is the x, and subtract the mu, or the mean, and divide it by the standard deviation. This is the population formula, which is exactly the same as the sample formula, just has different symbols. So again, what you do is you take your data point, you subtract the mean, and divide by the standard deviation to find the z-score. This is a z-distribution. We're going to look at many different distributions this semester. Each different statistical test that we learn has its own specific distribution. And the z-distribution is essentially what it would look like if you graphed z-scores, and it always has a mean of 0 and a standard deviation of 1. So let's look at a couple of examples related to height. When I was a kid, I used to get called the Jolly Green Giant because I'm very tall. So if we want to know how tall I am exactly, we would have to find out the average. And in the United States, the average female height is 164.8 centimeters with a standard deviation of 7.9 centimeters. And I'm 185.4 centimeters. So if we wanted to know where do I fall in the distribution, just how far above the mean or how far above the average do I fall, we could calculate a z-score. So here's our z formula. What we would do is plug in the numbers given on the last slide. So I'm 185.4 centimeters. We'd subtract the average female height of 164.8 and divide that by 7.9. And once you go through the math, you would see that my z-score is 2.61. What that means is that I'm 2.61 standard units above the mean. If we go back to our z-distribution, we could graph this, and I've done so by putting this red arrow into the picture. So 2.61 would fall approximately where that arrow is. So you can see that my score is beyond the 2 standard deviations, first of all, which means it's an extreme score, and that it is in the very, very far right tail. Another example, building on the first, is we want to find out maybe who's taller. height runs in my family, and my brother is 6'10". So if you wanted to know who is taller, we'd have to use a z-score. So my brother's 6'10" and I'm 6'1", and it might be tempting just to say, well, of course he's taller because he's 9 inches taller than you, Michelle. And that's true, but we have to take into account what the average height for each of our distributions is. Since I'm a female and he's a male, we come from different distributions. So we need to be able to compare his z-score to my z-score. So in the United States, the average male is 178.9 centimeters with a standard deviation of 8 centimeters, and my brother is 208.2 centimeters tall. So we'll go ahead and calculate his z-score, which would give us a 3.66. So we already have my z-score of 2.61, which is in the red arrow, and Kevin's score, my brother's score, is in the blue arrow, 3.66. He is extremely far into the tail of the distribution, so far so that he's actually off of this particular graph. So which one is taller? Well, the answer is my brother. Not because he's 9 inches taller than me, but because his z-score is farther above the mean than my z-score is. Another thing we can do with z-scores is think about the probability of getting a particular score on any test or in any scale, or higher or lower. So let's go back to the height example. We could ask the question, what's the probability that a woman would be taller than me? Or in statistics jargon, you could say this: the probability is a little p of getting a z-score greater than Michelle's z-score. So we know that my z-score is 2.61, but we need to be able to find out what percentage that's associated with. So we'd go to the unit normal table, which is in Appendix A on page 514 of the textbook. If you look up a z-score of positive 2.61, you would get a value of 0.9955. This value tells you what proportion of the distribution falls at that z-score or lower. Now, because we're talking about probabilities, you want to turn this into a percentage, which, moving 2 decimal places to the right, would give us 99.55. That means 99.55% of women are shorter than I am. But the question is, what percentage are taller than me? So what we need to do is actually subtract that from 1 or 100%, which would give us 0.45%. So the probability of a woman being taller than me is 0.45%.